let me first thanks to the organizers to give me the opportunity to talk to all of you about what it has been my main research project during my current PhD, and it is related to the dissipation-time thermodynamic trade-off in human decision-making. My talk will be mainly based in our preprint that you can find in arXiv, which is the product of a highly multidisciplinary effort between physicists and neuroscientists in ICTP and CISA here in Trieste, Italy. Let me start by telling you about the general experimental approaches to study perceptual decision-making. And let's understand perceptual as the identification and interpretation of the sensory information. So these approaches are basically to have study participants. You can have humans, monkeys, rats performing sensory discriminations with a sensory input being more or less degraded. And you can study this in several domains, for example, in the visual domain, in the auditory domain, and in the tactile domain. In particular, in the visual domain, usually participants have to decide if the net motion of a noisy field of dots is going in one direction or the opposite. In this particular example, they have an environment in which rats earn all their water by discriminating the direction of this kind of motion. But the thing is that human and in general animal daily experience is constantly bombarded by stimuli produced by non-equilibrium systems characterized by time correlations. So it extends beyond mere random dots. For example, driving, reading the road signs in a foggy day, the decisions that you made when shopping, or the decisions in financial markets. So we are interested in non-equilibrium phenomena. And here, in particular, we are interested in the visual perception of non-equilibrium phenomena with human participants. And our goal is try to understand how the process of the translation of the perception and the classification of the evidence into appropriate actions, into appropriate decisions occurs in the brain. And it is not trivial how the brain made this process. However, there are some mathematical approaches that could help us to understand the mechanisms of at least simple binary decisions. One of these approaches is the WOST sequential probability ratio test, which provides you with the optimal strategy that minimizes the mean decision time for given accuracies. So in short, consider a binary decision and the problem of guessing if a sequence of data is produced by a model H1 or a model H2, where these two models are two possible hypotheses. So you have two possible decisions and two associated accuracies in terms of these probabilities. From now on, I will consider the case of when these probabilities are equal, so we are in this symmetric case, and we are also considering this decision criterion that said that decide as fast as possible for given accuracies. In WOST SPRT, the decision maker is accumulating information until the weight of the evidence reach a given threshold, L or minus L, where this L depends on the accuracies. In particular, this evidence is given by the low likelihood ratio, given by this expression. So when this ratio reaches the threshold L before reaching minus L, a decision in favor of the hypothesis 1 is taken, and vice versa for a decision in favor of the hypothesis 2. So at the end, WOST SPRT is just a first passage time problem. In 2015, there was a work where they applied this test to a non-equilibrium stationary system. One example of this kind of system is a Brownian particle with drift. So here I'm representing the dynamics. In the horizontal axis, I have the overdamped Langevin dynamics with drift V and diffusivity D, and in the vertical axis, I only have noise, where H is a binary random variable that describes the direction of the drift. For this particular system, they were considering the thresholds at the distance of the Brownian particle to the starting point. In other words, they were considering the evidence accumulated as deposition. Also, you can characterize this system with the entropy production rate, the dissipation, that is given by this expression, as we, I think, already know. For this particular case, it is just B squared over D. And also, we can define a Piclet number in this way. Interestingly, they found that the mean decision time is given by this expression is inversely proportional to the dissipation. As this expression is giving you the mean decision time for given accuracies, you can understand this as a lower bound. So we designed an experiment in which we were asking to 21 human participants to guess the direction of this disk that is moving in a computer screen. We were asking if the disk was going to the right or to the left. This is the laboratory where we're implementing this result. I'm not sure if you are able to hear the sound, but the participants were hearing a sound when they were given right answers, correct answers, and an unpleasant sound when they were given wrong answers, just as a feedback. So the dynamics that is following this disk is the one that I already explained, but all this information is hidden to the participants. We explored 4 different experimental conditions. So we have 4 different entropy production rates. For each condition, we have 3 blocks, and each block contains 50 movies. And the information that we were collecting was the true hypothesis, the decision outcome, the decision time, and the physical position at the screen when the decision was taken. So now let me show you the statistics about this data collected. So first, mean decision time. So we have 21 participants, so we have 21 mean decision times. So with that data, I am building these bi-only plots. They are nice because they are showing the shape of the distribution, and this central horizontal line is showing the global mean. So we found that the mean decision time is decreasing with the dissipation, as the accuracy and the mean decision thresholds, the place where this was when the decision was taken, was kept more or less constant across conditions. So now we can compare our experimental results with the predictions by WOST PRT, and this is what we found. Here, the empty bi-only plot corresponds to the predictions by WOST PRT, and the colored ones to the experimental data. So at least qualitatively, we have a good agreement between theory and the experiment for both mean decision time and also accuracy. But our colleagues from cognitive neuroscience were not that happy with these results. The thing is that from the cognitive neuroscience viewpoint, the process of the evidence accumulation entails mainly 2 aspects. First, retaining a recollection of the previously accumulated evidence, and then incorporating new evidence into the existing memory. And WOST PRT doesn't offer an explanation about these memory effects. Moreover, WOST PRT predicts that you have fixed thresholds. So when you see the probability density of this X deck, you should expect to see something like this. But what we really see with experimental data is a whole distribution with certain variance. So in the light of our experimental results, and also taking into account the cognitive neuroscience perspective, we develop a new model that we call evidence integration model, in which the evidence is going to be accumulated in this new decision accumulator, W, where tau m is a parameter that we call memory realization time. And here we have a memory kernel, an exponential kernel, that is including the effects of memory. When tau m is equal to 0, we recover the position, and we have this gray line in this plot. No? So this W is acting as a filter of the position, because as we can see here, it is reducing the fluctuations of the trajectories. So also we can write this equation in terms of a differential equation, and we end up with an underdamped Langevin dynamics. So we also need here a decision criterion. Basically, here is the same that I already explained by WOST PRT, but in this case, we have W, that is the evidence that is going to be accumulated, and we have these thresholds LW and minus LW. We also assume that each participant have intrinsic parameter values for tau m and LW. I am not going to enter so much in the details, but basically what we did was fit the mean decision time. So this solid line corresponds to simulations from this new model, and the dashed line to the experimental results. So we are going to choose the tau m that fit the experimental mean decision time. And we did this for the 21 participants in all conditions, and that's what we obtained. So we see that this parameter, this memory parameter, is increasing with the dissipation. So we expect that this model can in some way try to model the outputs of the human brain. So let's see. So here I have the joint histograms of the X deck, that is the position of the disk when the decision was taken. So here I have all participants, all conditions. This red line represents the perfect match between theory and human answers. And as we can see, evidence integration model, it is giving you better predictions when you compare with WOST PRT. Also, this support by the Kolmogorov-Smirnov test. And it has happened the same with the decision times. Evidence integration model is giving you better predictions. In fact, WOST PRT is giving you faster decision times with respect to the human responses. So there is kind of a suboptimality in human responses, no? This suboptimality can be maybe better understood with this figure, where I am plotting here with this black curve, the theoretical bound that was predicted in this paper in 2015 that corresponds to WOST PRT. So now when we plot the experimental results for both, participant by participant and also all conditions, that's what we obtain. So humans are obeying in a very, very nice way this bound. So I think I should be more or less out of time, so I will leave you here with the take-home message.